Yeah, I will start around 6:45. Okay. So this week, yeah. Yeah, we will start around 6:4, 6:5. So please wait. Yes, so we will start now. So today is 14 February. I am Prashant Kumar, a PhD scholar at IIT Kanpur. I will be taking this fourth week tutorial session. Okay. So in this week, the major topic was the optimization and the basic of neural networks. So how the neural network has been created, what was the idea, and how it has been came into the picture. So we will talk a little bit about optimization, a little bit detail more than what is there into the lecture, and then we will solve some problem, and that's how this week is it is going to. And since we have not been introduced kind of loss function or kind of you can say overall training process, but if you like, I would like to introduce you to some code, some small, um, you can say the minor details about this optimization and what kind of training happens, how the error propagates, how the error creates problem, and some kind of a random solution. How much actually you can optimize your solution. So this kind of thing we can discuss more with the code. So first we will discuss some topic, then we will go through some problem. And if we will have time, we will discuss code as well. Okay. So let's talk about this optimization. So in general, when you studied the mathematics, the basic optimization that you studied was like, let's say you have some kind of function that is y given x, and you have been told to find the global optima, right? However, so let's write y as a function of x. And then what you do? Basically, when you try to find a random x at I equal to 0, that is called iteration at 0, given let's say this one, x0, and this is let's say xn, that is the optima, and you are trying to reach the optima. So the idea is to reach the optima by multiple methods. It can be either shooting method, or it can be Newton's method, or it can be uh, like the Hessian method as well, but that is a second order method. So what you do, you take you take the initial x naught as the initial guess, you find the y, and then you perturb the x naught by plus minus delta x, right? And if x naught plus delta x is lower than f of x naught, you say that you are basically moving towards the optima, right? Then this is the correct way of moving, right? If f of x naught minus delta x is uh, greater than f of x naught, this is not the path you want to take, right? This is more like a shooting method. So you have taken the x and you just perturbing your initial guess and checking, are you moving towards the optima or not? Or what you can say, or you take this slope here at x node, and you are saying that since this is the positive slope, this is the negative slope. You remember, okay? x1. This is a positive slope, this is a negative slope. Yeah. So if this slope is negative, you want to move into the positive direction. This is the negative slope, positive direction. Okay. So in this case, you are talking about the derivative. So basically dy by dx, or you can write d of fx by x. Uh, yeah. And in this case, you have a function that is purely doing the optimization to reach near the minima. So what is happening basically, take a little bit of finer look in this case. Let's make another diagram. You have a fixed function that is very smooth. You took the slope, you and let's say you are taking moving to the negative of dy by dx, but you are taking a small portion of that. So you are multiplying with some number alpha that is less than 1, right? And then you have moved somewhere here. Then you again took the slope and moved again, because now the slope is becoming smaller. So you are moving smaller, keeping the alpha constant that is less than 1. And since you will be moving here, even the alpha will be constant. What will happen? The slope is smaller, so you will be slowly moving near the optimum. Or if you are keeping this alpha constant, you will be, after infinite iteration, you will approach towards the optima. This is the pure optimization, right? You have a function, you know the slope is always going in the direction of optima. This is what you are going to get. So we are calling it as a pure optimization for right now. So why it is pure, we will discuss about it later. Now let's talk about the machine learning optimization. So before we talk about this, whatever we want to optimize, that is the loss function or the cost function, let's discuss a little bit about the cost function itself. Okay. So basically, this is your x, this is your y. You know that y is a linear function of x. So basically, you have some relation like this. This is linear. And you can write this as a mx plus c, where you don't know m and c. These are unknown. M comma c. Okay. Now let's take another. Let's assume an experiment, like you are doing some real-time experiment, and you know from the previous relations that whatever you are doing for some input x, the y you will be getting, that should have a linear relation. Okay, something like this. Okay. However, in your experiment, there will be always some kind of error. The error can be human error, the error can be the machine you are using, the machine error, or any kind of error. Okay. So ideally, for given x, you should have gotten this linear relation, like you should have gotten this y for given this x naught. For x1, you will get something like this. For x2, you should get something like this. Right? It's a little bit lower. Okay. However, so you did experiment, you got some result, and the result is this one. Let's create this. This is your result. you changed the input, you got some right here. You got this result. You change this x2 again, you got some here result. You got some kind of result. However, you can see that you are moving along the line of this linearity, but you are not on the line. So always there is some kind of error. Even though you have calibrated your experiment, there is always chance of getting the human error, right? So you got these results. Also, there is also another point is that let's say you have given the x node, you have got some result. Now let's do the same experiment again, and you got something here. You did the experiment multiple times, 1,000 times, and you are getting some results here around this point. This can always happen, and in that case, you will say that this is your giving this X node as an input and getting the results different each time. And let's talk a little bit like this. So this is your X node, and this is what you are getting Y node. Okay, this is your all these Y nodes. Okay, now assume your original Y node is something like this. This is your original Y node. Let's say this is your original Y node in case one. Let's call it case one. Then what is happening? Basically, you are getting the solution and you always have some kind of bias in your solution. Okay. So this is of a kind one bias. I don't remember the name right one. So let's write kind one bias. Now, let's say you have a different machine, but they also perform in the similar way. And they are also doing the same thing, but like you can have a in your factory or in your you can have a multiple machine doing the same thing because you have multiple users, and some other user is getting the results here, right? So in this case 2, you are getting the error, but your mean error is almost near your correct value, right? So here you don't have the bias, you have some variance, and that is creating some error, but still your mean of that case 2 is almost 0. Okay, now keeping this information in the mind, now let's create a loss function. In that case, like we come to this experiment, you know that your relation between input and output is mx plus c. You don't know the value of x, you don't know the value of c, but for all xi, you have some yi. Okay. And you have done some m number of experiment. And you have got this data that tells that for all xi, yi, for all xi, you have yi, and that are the total number. That are the total number that goes from I goes from 1 to m. Okay. Okay. Now, what you are trying to say that you want to find the value of m and c for this given yi and xi. Okay. So you created the value y of now, like you have some in random xi, and for some random m and c, you got the yi, and then what you said From the original relation, let's say you also know your original solution that for x node, for xi, your y should be capital Y. Let's call it a small y. And your correct solution is yi. Okay. So this is what you are inducing here. These are the errors for given this correct yi for which the m and c satisfies. Like like you have m naught plus c is c naught, that is equal to y. This is your correct value. This is what you have got from the experiment, and you want to fit the value of m and c such that you have got the value of m and c as m naught and c naught. Okay. Now, for any m naught and c naught, this is the minimum error you are always going to get, right? Anyone? Are you listening? Hello?
Yes, sir.
Yes, we are listening. Yes.
So
Somehow
I'm
we
saying
see
that
some
you,
we see some pop board actually GN or DP. I don't know. Can you remove that, please?
this one.
On the yeah. Thanks.
Let me see. I have to check. I'm not sure how I should change this.
Maybe you can just minimize it. That's all.
Is there an option of minimization? I'm not sure. If I will cut this, I don't know it will. Oh,
Yeah.
okay. Yeah, it is still there. Oh, sorry.
Yeah.
I was afraid it will cancel. Okay. Yeah. So I was talking like even you got this M node and C node, you are always going to get some error, and these are these error, right? And these are the minimum error you are always going to have even you get this M node and C node. And that error is basically uh, M node. Sorry, you can write yi minus yi. And these are the error you are always going to get. Let's write the absolute error. Otherwise, some error get cancelled and you will say that there is no error. However, there are always error. Okay. Where I is equal to 1 to m. And let's take some mean. So we are calling it this as a mean error. And these are never going to go to zero. This will be near zero, but it will never be zero. Right? Q. Oh, sorry. Why? Because of the stochasticity of the experiment. Stochasticity of the experiment. Now, what you are doing, you are assuming in this case that you have got only the linear relation. Okay. If you are training any neural network, let's, when I am saying neural network, I have not introduced till now. Let's call it as any function that is non-linear, and it can fit any data. Okay. When I am saying it can fit any data, means if you have XY relation, if you have some number of points, basically it can create such kind of line. And this is the NN of x comma theta, where theta is the parameter, x is the input, and this is what it is trying to fit it. Okay. Understood? In this case, you will say that the error is 0. However, from the experiment, you know that the relation is always linear. So basically, you are overfitting the experiment using the neural network. Okay. Now, this is, let's call this as the overfitting for right now. I am
Sorry,
just throwing.
what do you mean by overfitting?
This is not, this is the overfitting. Yeah. So you did the experiment. You know that the input output relation is always linear. However, when you trained a neural network, calling this function F neural network for any input x and theta, it is exactly following the whatever the y you have got from the experiment. Okay.
Okay.
So from the knowledge you have, you know the science. From the science, you know that the relation between an x and y is always linear. But when you have tried to train this neural network, when you have tried to train this parameter theta, you have got this relation, right? And now that relation is basically fitting it. And now let's say you have some input new x new, and you are trying to predict the value of x new. Let's say this is x new, and not here. Let's write somewhere here. X new. This is what you are going to predict it, right? Because this is what you are fitting it.
Right.
But ideally, this is what you should get with some margin of error. Like when you know that when you are training any neural network or any this y equal to mx plus c, where m and c are the parameter, you will get some error, but that error should lie into certain range, not this range, right? So this error is too much. And basically you are saying that when you have trained this neural network, you have overfitted the data rather than generalizing the data. Okay. Understood?
Okay. Yeah. Got it.
Yeah. Yes. So after understanding this much, let's formulate a loss function. And that can be, currently I am writing the loss function as a mean square error. That can be written as sum of whatever the output you are getting, that is m of xi plus c minus yi square from I is equal to 1 to m divided by 1 by m. Square.
Square root of that, right?
What?
Square root of that, correct? No.
Not root. Currently I am writing the mean square error. I'm not taking any root right now.
Okay.
Why I'm not taking a root or why I am squaring it, the idea is either you can take like if I am squaring it, I am saying that let's say one error is plus 1, another error is minus 1, the third error is plus 0.5, another error is minus 0.5. If I will
You want
add
to
all of them,
ignore
it will
sign.
become 0.
Yeah.
Right?
You want to ignore sign. Yes.
Yeah. And basically all of them are error. If I will add directly, it will become 0 and I will not able to train the network. Or I will not able to train my parameter. Forget about the network right now. The parameter is MNC. Okay.
Understood. You are not interested in sign. You are interested in the
Overall
quantity
error.
or value. Yeah.
Yes. Yes. So I can take the absolute value. That should work as well. Right.
Yeah, that's right.
However, taking absolute value basically creates some kind of linear relations. Okay. And in the optimization, when we think about anything, we are assume that we are doing some kind of convex optimization. What does it mean by convex optimization? Basically, when you have any function, and if you are taking any 2 point in that function, and when you are creating a line, it should not cut the function anywhere in between. So this is a non-convex function because it is cutting here, right? If I will take point here and here, it is not cutting. But it does not mean that this is not cutting in this case, right? So this is a non-convex function. If I am taking, in this case, I am taking points here and here, I am getting no, this line is not cutting this function in anywhere in between. So this is a convex function. Okay. So idea of squaring is to get this function kind of convex. It's not that it always will, but we will try every approach that will create a ideal scenario for my optimization. Okay. Okay. So now we have done this mean square error. We have got this loss function. Now we can basically create this, we are calling this L, and we can always find this value of dou L by dou M and dou L by dou C. And we can do the iterative approach, right? For training M and C until we say the MT minus MT minus 1 is less than delta, less than epsilon, let's say, and CT minus CT minus 1 is less than a, right? So these are the condition where I want to stop my optimization. Okay. Now, when I was talking about the machine learning optimization and the pure optimization, what you are going to get here? When let's draw another line, and we are saying that this is the M and this is the L. Okay. Similarly, you can draw some curve for uh, L and C. Okay. When you have changed the value of M, when you have changed the value of M by some value, basically it might happen that somewhere the error will become larger. Let's say, let's draw another picture. So this is where your points, these were your points. The originally, when you assumed the value of M and C, this was your overall error. And you have changed the value of M from this to this, right? You try to move some in the direction of less error, and this is your direction. What happened? It might happen that somewhere your error has become smaller, but somewhere your error has become larger. Okay. In that case, what will happen? You will come here, but when you will reach near the optima, like when you are almost your M minus M nowadays is less than some 2 epsilon or something like that. In that case, what will happen? There will be always some kind of fluctuation rather than reaching the optima. Because you are always trying to find the error for a lot of points, the M points. Okay, I should call that K points. So this is basically okay. You understood. Like when I was telling the endpoint, I should have called something else. So when I am trying to create the error to for all those key points, every time I will change some value of m, the error will little bit error can fluctuate. And in that case, because there is a stochasticity in this error and it cannot go to the minima, there will be always fluctuation near the minima. You understand that, right? Because error is
Mhm.
not zero ever. Understood?
Yes.
So again, I will repeat, because there is a stochasticity and error will never go to zero, you are always going to get some gradient near the optima, and in that case, you will be keep fluctuating near some m naught plus epsilon and minus epsilon, and you will never reach to the m naught. So your basically result lies between in this range. Okay, so that's why this is called as a machine learning optimization. This is not the pure optimization because you are not never going to reach the optima, because whatever the data you have, that has some level of stochasticity. Okay. Okay. So now we have understood the optimization in the case of machine learning. Let's talk little bit about this batch optimization and mini batch optimization. This is pretty much theoretical. Now let's say now you have 100,000 data. That means you have a data that has the pair of xi, yi, where I is 1 to 100,000. Okay. And when you are doing this optimization, and when you are calculating the loss or xy from p data, we are calling this as a f of x comma theta comma yi. This is the L. It can be MSE or mean absolute error or whatever, or logistic regression and other thing. In that case, this is I'm calling this as a loss. If you are taking the error for all this 100,000, you are taking the mean or whatever, basically you are incurring a lot of computation in each iteration. And every time you are taking a gradient of theta with respect to theta for L, you are doing this all the computation for 100,000 points. Okay. So what can happen in this case? Every iteration is very costly. This is the first thing. However, since you are taking the mean for all the 100,000, the gradient is going to be very smoother in a sense that the L versus epoch or iteration, let's call it iteration for now, this is going to look very smoother. Okay. And this is the basically threshold value to which it will never go down. Okay. Okay. This is for the batch. So what is happening? You are getting a smooth optimization, a smooth loss versus epoch graph, but you are incurring a lot of uh, computation in each iteration. Okay. Now let's talk a little bit about the mini batch and then we will compare it again. You have 100,000 data, but you are saying that you will optimize this function or the loss function, this L of f of x comma theta comma y for all the x, y from the P data. P data is basically a kind of distribution from which you are picking x and y. Okay. So for 100,000, you have made 10 batches in which each batch has randomly chosen 10,000 points. Okay. Why I am saying randomly chosen? Let's say you did some experiment and your experiment was some sequential experiment in which you went from x1 to x0 sequentially and you took all the data for all the x1 to x1 in a sequential manner and you because you want to not mess up with your mind in a way that you want your experiment to be well understood for you. And then you took first 10,000 as a one batch, another 10,000 as a one batch. So basically, let's say this is your experiment. And ideally you want to get this, but you have made the batch something like this. So what will happen? The first will try to create this, the second will try to create this, and third will try to create this. Every time you will fit that 10,000 point for the optimization for M and C or the theta. Let's call it theta for right now. In that case, you will incur the fluctuation every time you will give the this 10,000 point in your mini batch. That's why we have to randomly choose the 10,000 point, and for the all the 10,000 point, the distribution should be the same. Like if I have 100,000 point, and if mu and sigma are we have got from this, the mu and sigma for the 10,000, it 10,000 should be same as well. Means near to whatever you are getting. So basically, you are saying this as a identical, independently and identically distributed. Okay. And in that case, your loss will look something like this. This is for the mini batch, and this is for the batch, full batch or something batch. Let's call it batch. So which is better? Since you are calculating 10,000 mean, point of 10,000 mean, basically this is less costly. So both has its, the advantage is that it is less costly. There can be another advantage is that sometime, let's say you are figuring out the optima. I mean, since you have some graph, this is your optima, this is your minima, this is your minima, this is your maxima, this is your global optima, global maxima, this is your global minima. In this case, when you are doing overall optimization, it might happen that you might get stuck in the some minima than global minima. But currently you are taking a stochastic kind of loss in that case. And if you are doing the mini batch, it might happen that the more point that you have taken are near this. I mean, we are assuming that this is IID. However, it can happen that some points create larger loss in this region and smaller loss in this region, and gradient might go in this region, and you tend to get a better solution in the case of mini batch. However, your mini batch should be optimized, and there is no uh, any mathematical way to get the optimum mini batch. You can play with your batch size, like what is good, how much mini batch your computational facility can take. And like let's say 100,000 is not more than big. I mean 100,000 is big enough for your experiment. I mean for your computational facility. Like let's say you have a computer of RAM 32 GB, then it's fine. Otherwise, you will have to take batch, and there are different training methods. Like sometimes people choose to train for all the points as a batch, and later they want to basically switch to the mini batch, because they tend to think in a way that initially I have created a trend, but the trend is not good enough. I want to reach the optima faster, so I need to perturb the data. And perturbing means you are taking a small mini batch. I mean, you are taking a mini batch. So perturbation doesn't mean you are trying to change the value of M and C, or you are trying to. That is also a method of training in which whatever you have got, let's say you have got this trend, and you know that somewhere you have stuck in between. So you basically perturb the value of M and C by some epsilon or some sigma, some variance, because you have a lot of theta or a lot of M and C. In that case, it might happen that your loss will increase for some time and it might decrease then after. So there are a lot of training tricks. I will call it tricks only. Like start with full batch if you can, then move to mini batch, or you can say a smaller batch, or perturb. Perturb means slightly deviate from whatever the points they have. Like let's say your M and current M and C has some mu and some sigma. After knowing mu and sigma, you can basically perturb the mu by some value like mu minus mu naught or something, and mu naught will come from the idea of sigma. Okay, perturb the M and C. I mean, you can. These are some very good training methods. Okay. So now we have talked about whatever the method that was, that is called stochastic gradient descent. So we were not assuming any fashionable way of reaching to the minima. We were taking simple gradient, and we are trying to move in the direction of optima, or trying to move where the gradient is, I mean, the loss is minimum. However, there are method called the momentum based method, in which you improve your stochastic gradient descent by adding some momentum. So what is called, okay, just a minute. Okay. Yeah. So what is called momentum? If you know the physics, you basically say like when there is some mass and it has some velocity, you multiply with that, and that is the momentum, right? So here we are saying that whatever the loss that I have got, that has the mass of, that has the unit mass, and the velocity is basically the gradient. Okay. So during the stochastic gradient descent, we were saying that my theta t plus 1 is actually theta t minus alpha of g t. Okay. Where gt is 1 by m of gradient of theta of I is equal to 1 to m of loss function f of xi theta comma yi. Right? Okay. Now we are saying that we are adding the term velocity. So, and velocity is related to gradient. So
Sorry,
now
here,
what?
sorry to
Yes,
interrupt.
yes.
Here, yi is the classes, right? Or
Yeah,
accordingly?
it is the output,
Class,
the classes. If
output
you are doing
classes,
the
right?
classification problem, this is the classes. Yes.
So whatever 100,000 samples you have taken, vectors, correct? That you
Yes.
want to classify within this yi. So I ideally that should be j, right? Something yj, because not necessarily that we would like to put these 100,000 into the same number of classes. For example, those 100,000s could be pictures of cats, dogs, or anything, but we would like to classify them into three or four, say for example, cat, dog, or aeroplane, or anything, right? So there, why not necessarily should be I, isn't it?
Okay. Okay.
So why should
Just
be means it should not be I, it should be something else, j or any other variable, which is much smaller than your training vector, correct?
no, no. I got your point, what you are trying to say, but you have to simply think that for every I, for every X, there is a Y. Let's say you have a
Mm-hmm.
100,000 data.
Mm-hmm.
The Y, like let's say the first image has some cat, the second image has dog, the third image has cat, fourth image has dog. But
Mm-hmm.
that cat and dog is their respective output. Okay.
Mm-hmm.
You can say that there are different k outputs for I number of input, but I am saying that I am trying to calculate the output for their, I'm trying to calculate the loss for their respective input and whatever the input the output have. Okay, so
Okay.
basically, so when you are creating a data, you are creating a pair of xi and yi, and it can be m numbers, right? You
Mm-hmm.
understood what I mean?
Yeah, means you
So
mean to say, for example, the data could be an image which has where x, y are the pixels. It could be anything, correct?
yes, and
Correct.
it is a image, let's say in your case,
Mm-hmm.
and it is their respective output can be dog or cat. Let's say for right now I have two output.
Mm-hmm.
So this dog is the output for xi. Let's say xk is the input, the yk is the output. Yk can be either a cat or either a dog, but it is their output. It is not
Okay.
their others output. Understood?
Okay.
If
Yeah.
if I will write something m here or something j, it won't know it is the output, but it won't know it's his output. Like when we provide this xk to function f, it doesn't know how to calculate that error. Understand what I mean?
Mm.
While classification, you will get the k output. That is a different thing. That we will. I mean, that in the support vector machine, you write the k output view because you want to create a linear relation. Okay. Assume that there is no linear relation for right now. And I am not talking about the number of output for right now. I'm just trying to create a loss function. Okay. At least this one is clear, right?
Yes.
This yi is there. This yi is for the respective xi. Either it can be dog or it can be cat, right?
Yes.
This is clear, right? Okay.
Yeah.
Yeah. So I was talking about the velocity. Okay. So initially, I am assuming this kind of optimization, and we are calling it as a stochastic gradient descent. Now I am saying that I am trying to add momentum to my process of trading, and that momentum comes from the gradient. Okay. and we are calling that momentum as a V. Okay. So I will just see that whatever the process here that is happening, uh, alpha is basically the learning rate or the how much far I want to go into direction of the gradient, opposite direction of the gradient or the direction of gradient because I am taking minus here. So I am saying that I will create this as a theta t plus 1 is equal to theta t minus alpha gt plus let's call it beta v. And what is v? V is actually uh, sum of previous gt. Let's call it. Let's write v only. Let's write beta here. Like for t less than t plus 1. So basically, you are adding all the gradient from the previous iteration you have done. You have multiplied with some beta, and you are saying that whatever the gradient you have got, you are basically enhancing the gradient with the previous gradient you have. The part of the previous gradient because you are taking the beta where beta less than 1. Okay. And this is called the gradient. Sorry, momentum. So this is the part of the gradient. You are taking the current gradient and sum of the previous gradient, and this is acting as a momentum to your current gradient. So it will enhance your training. It will hasten up the training, or it will not fall into the global optima, local minimum. What I'm saying. So it will not fall into the local minima. So let's take an example here. Let's take a simple example. This is your, you have started from here. You took the gradient, you reached here. You took the gradient, you reached there, but the gradient you are getting here is almost 0. So basically, you cannot reach here, right? However, this is your correct result. So what you are doing, basically, you are recording their previous gradient. So whatever the gradient you have got here, you use that gradient to move from here. You earlier you were reaching here, but from here when you calculated the gradient, you use some part of previous gradient, and instead of reaching here, you reached here. Okay, you calculated the gradient. Maybe you are getting the 0 gradient, but you already have your previous gradient as well, and you might come here or here or here, right?
Mhm.
And since you are using your previous gradient, you are using the momentum. Assume is like you have a bowl. You have a bowl here. This is a curve, and this bowl is rolling over this curve. And since this bowl is having a 0 friction or minimum friction, this bowl will have the momentum, and it will like not. Let's consider some friction. So basically, it will come here, but it will have a lot of velocity. So it will go up again, and it will come down. Right.
Mhm.
So basically, this momentum, this previous gradient are analogous. Okay,
Okay. Mhm. But
understandable?
yeah, but one thing, do we know the range of this function? For example, from where to where we have to find the minima, optimal minima. In that case, won't Lagrangian work? Or
We are talking about the stochastic, right?
yeah.
So when you are talking about the stochastic, you are not using your previous gradient, and you are saying that you will be, if there is a saddle point kind of thing here, in that case you will go to the optima. But if there is not saddle point and you have some kind of this kind of peak, then you will keep moving near this. You have a stochasticity, but you will not able to move upward. Okay,
Okay.
understood? Logical? Logical enough?
That is correct. But what I'm saying is Lagrangian function, right? That can help us, right, to find the minimum value of a function if given a constraint, right?
What does it mean by Lagrangian function? Can you explain?
Like say f of xy minus uh, right. I have taken a note once again. Once again, I'm showing you.
Yes. Explain.
Yeah. May I share my screen for a minute?
Yeah, let me close my screen.
I can share no problem, if you allow. Yeah.
I think you are allowed to
Yeah.
share, but I think I will have to close my right. Close mine.
No, it's okay. No need. No
Okay,
need.
okay, okay, okay.
You
Yes.
can see. So
Just
this is the quick calculation. For example, minimize f of xy. For example, they have given example x square plus y square and subjected x
can
plus
you
y is
zoom it?
all. Yeah, yeah. I can zoom. Yeah. For example,
Yes. Yes. Go on.
now they have given a function say f x y where x
Hmm.
square plus y square and given x plus y should be always 1. So in that
Okay.
case, they are using Lagrangian function say L is equal to x square plus y square minus lambda of x plus y minus y. This should be 0. So x plus y minus 1. Now when we take a derivative of L with respect to x and as well as lambda and
Hmm.
equal, then it will solve that it will give the value of x and y, which is the perfect value, like no iterations. But
Okay. Okay. I
but
understood what you are trying to talk. Yeah. Yeah.
but
Yeah. Go
here
on.
probably we don't have the equation, correct? That's what the problem.
Yeah.
Because
So
it's a stochastic
exactly.
signal. Yeah.
Yes. Exactly. I was talking about the difference between the pure optimization and the machine learning optimization.
Hmm.
Understood.
Yeah,
So
yeah.
also, you don't know what kind of Lagrangian you want here because you don't know the curvature of your optimization
Hmm. Okay.
because M and C are the random, right?
Yeah, yeah, got it. Sure, please carry on. Thank you.
Yeah. So can you? Yes, I will have to share. Yes. So I was talking about the momentum, right?
Hmm.
Yes. So let's write negative of it because still we are using the gradient in the direction of the optima. So we have to check the negative here. Okay. So this is the one kind of momentum. Then there is an improved version of momentum that is called nest array of momentum. Okay. So what happens? So whatever this gradient we are using for the overall optimization, in the loss function, we are saying that, let's write this again. So 1 by m of gradient of theta of f of x comma theta comma y, right, plus v. This is the overall, I mean, this is take epsilon plus v. Okay, and then you are taking the negative and everything. So the Nesterov is saying that while doing this optimization, do a little bit change and do the optimization, add a little bit of velocity in the this function as well to even shoot the optimization. And basically the momentum also comes with some kind of stochasticity of the training. Okay. Sometimes it might overreact. So this overreaction can be reduced using the Nesterov momentum. Okay, because this gradient is used, this velocity is being used to update the theta. So you can use that theta to reduce some theta. I mean, here we are using the addition because it has some negative values. Basically, it will reduce some theta and it will basically stabilize the overall the gradient path or the optimization path. Okay. And then there are the second order method. There are also the other some first order method that is called Adam. Then there are second author called the Newton's method for the second order. And then LBFGS, long memory, BFGS. These are the four scientists. These are the second order. If you want, I could explain this as well. Otherwise, let's talk a little bit about the neural network. And if we will have time, we can discuss. Maybe if you want, I can discuss it in the next week. Okay.
Sure. Yes.
Now, so let's talk about the neural network. When we talk about the neural network, we talk about the perceptron. So perceptron comes from the idea of the neurons in our mind that takes some input and provides some output. And if we just vaguely draw this image, it has some input feature. I mean, this is what the people assume. So these are the input nodes. It has some nucleus that will process it and it will give some output. The inspiration of perceptron comes from here. So input can be n number of input. And you can have a m number of output because it is giving output. It can give them multiple outputs. Okay.
Right.
Right now, let's assume. Let's make a simpler figure in which you are saying that a neuron takes the input, perceptron takes the input and produce some output in which these inputs are x0, x1, x2, x3, output is y, and relation is that for each input I have some weight, let's call it b for right now, and it will produce some output, and that output is x1 w1 plus x2 w2 plus x3 w3 plus x naught into b. Okay. There are more to it, but before going there, let's see if this perceptron can solve any nonlinearity as or not, because this is a linear relation. This is a OR node that taking multiple input and producing some output. So let's take a OR gate. It has two input x1 and x2, and the output is y. If it will take 0 and 0, it will have the output 0. It will take 1 and 0, output will be 1. It will be 0 and 1, then output will be 1. It is 1 and 1, output is 1. Right?
Mhm.
Now let's write. I have a x1, I have a x2. This is the 0. If I am taking 1 comma 0, this is 1. This is 1. So basically 1 here, 1 here, and 1 here. So basically you can see you can easily classify using a simple linear line, right? Between these two this OR gate. If you have a AND gate, x1, x2, y, 0, 0, 1, 0, 0, 1. So this will be 0, 0, 0, and 1. Right? So it will look something like this, 0. It will be 0, 0, and here it will be 1. So something like this will basically classify it. So this equation might look like x1 plus x2 minus 0.5 is equal to 0. And if x1 plus x2 minus 0.5, let's say if it is fitting or not. If I will give 0, 0, it will become negative. If I will give 1, 0, it will become positive. Right? So this is positive area, this is negative area. So basically, in this case, here the W1 is 1, W2 is 1, and B is minus 0.5. Right? So, okay, let me.
So B is bias, is it?
Yes. In this case, I can write X transpose W is equal to Y, in which X is
X1 to
X1, X2, and 1, and W is 1, 1 minus 0.5, right? In this case, right?
Yes, you're right.
And if Y is greater than 0, then it is producing 1. I mean, W transpose, let's write W transpose X is greater than 0, Y is positive. And if W transpose X less than 0, I mean, obviously, the Y is 1 and the Y is 0, right?
You mean classification, right?
Yeah,
Classes.
simple classification. Okay. In this case, it will look something like x1 plus x2 minus 1.5 is equal to 0. If you are taking x1 and x2 is equal to 1, then it will become positive, that is 0.5. And if you are taking 1 or 0 or 0 or 0, it will become negative. So basically, here W X transpose W, or X is equal to x1, x2, 1, and W is equal to 1, 1 minus 1.5, right? So in this case, the classification is linear, right? Now let's take a XOR gate. So XOR gate, in this case of XOR gate, you have x1, x2, and you have output. If you are taking 0, 0, it will produce 0.
0.
If you are taking 1, 0, it will produce 1.
1.
It will 0, 1, it will produce 1. And if you are taking 1, 1, it will produce 0.
0.
Right?
Yes.
So this is 0. This is 1. This is 1. And this is 0. In this case, you say you cannot have a linear line to classify this, right? So basically, you are having two lines to classify this XOR gate. In that case, you have a two input, x1 and x2. So you can, in this case, if you are using one perceptron, you cannot classify this problem because you have two input, two weights and bias. So basically, you can only create a line, but you need two line, to create this classification here. Okay. In that case, you will need more than one perceptron. It can be in the parallel fashion or it can be into the uh, serial fashion. What does it mean, parallel and serial? We will talk later. And then we will be able to give some input and it will produce the JOR. Okay. Basically, we are calling it as JOR. When we will give this input 0 and 0, it will produce this value. Okay. So what can we do? We can say that let's create this graph again of x1, x2. And let's create x1 plus x2. This is 0, 0, 1, 0, 0, 1, and 1, 1. So if this is x1 plus x2, it will become 0.
0.
This is and, right?
1,
No,
1, 1, 1.
this is OR, sorry. Yes. And if you are saying NAND gate, that is x1 dot x2, then it will
1,
become
0, 1, 0, 0.
1. This will
0,
become
0, 0.
1 NAND. So
0,
it will
0,
0.
0, 0.
Okay. And you can basically write this as a x1
X1
plus,
bar plus X2 bar.
right? So let's write this for right now like this. And if you will multiply these two, means if you take the end of that, I'm not sure if I am going wrong. Let me check.
It will be X1 bar into X2 plus X2 bar into X1, because X1 into X2 bar will be always 0. Same for X2.
Yes, I have to do something else here, right?
No, it is correct.
No, no.
And right.
So
And is
this is
X1 plus X2.
this is OR, right? This is OR.
This is OR. And it means dot. X1 into
Yes.
X2.
I think let's do it dot here, I guess. I think it is dot. I'm not sure.
Yeah. Yeah. And there also it is dot. NAND also X1 into X2 whole bar.
Yes, yes. That can be
Which is
written in this
equal.
case.
That is correct. That is equivalent to X1 bar plus X2 bar. That is correct.
So let's write this like this. And this is correct.
That is correct.
Uh,
When both are 1,
and,
then only it will be 1. Yes, that is correct.
and if I am multiplying it and then taking the, I mean, there are multiple ways to do the same thing. Like
Multiplication will
what
be
you can
always
do
0.
if you want to
Multiplication will
produce
be always 0, right?
what?
If you multiply x1, x2 and x1 bar plus x2 bar, then multiplication will be always 0.
Yes, yes. So I'm saying, so let's add these things and then take the negate that.
Mhm.
So what will happen? If you will add these two, it will become 1, it will become 0, it will become 0, it will 1. And if you will negate that, then it will become 0, 1, 1, 0. Right? So basically, you can write this as a x1 dot x2 into x1 bar plus x2 bar and then whole negate. Right?
So the final one will be x1 into x2 bar plus x2, x1, x2 bar into x1, something like that.
What you told? Can you repeat?
So if A and B are the input, so A into B bar plus A bar into B. That will be the XOR gate, right? If these are the, here you are saying x1, x2. So
Yes, yes.
x1 bar into x2 plus x1 into x2 bar.
You're
X2
saying
bar.
this, right?
Yeah, yeah. The final one.
Yes, so overall it will become like this, right?
Yes.
Okay. So
That is correct, right? That's what you were saying.
yeah, it should be correct. I mean,
Yeah.
it doesn't matter. What I am trying to prove it is that I want to create this XOR gate using the multiple perceptron. Okay. So basically I have one perceptron. I have another perceptron. I took some input here. I mean, I have an input x1, x2, and then I have a one bias. So this input is going here. This input is coming here.
Yes.
And then you have a bias for like you have two biases. And let's call it one. And this will be W1 and this will be W2. I mean W11, W21. This will be W21 and this is W22 and this is B1 and B2, something like this, or B1 or B2, right? And once you are whatever the output you have got that, you are giving this output to
Another
another neuron
perceptron.
with some bias, and that
Bias.
is producing the XOR gate. Okay,
Got it.
let's call it as A1, A2, and this is the B node, something like that. Okay, so idea is that if you are taking a perceptron that is linear, these perceptrons are the linear, right? These are the linear
Yes, sir.
perceptrons.
Yes.
They are the linear perceptrons, and if you want to classify something that is not linear, you will need more than one layer. So you are calling this as a layer one,
You're right.
and this is
Second
layer
layer.
two. To create the non-linearity, you need more than one layer. Okay. In the case of linear perceptron.
How many layers we can add actually for the specific XOR gate? Minimum.
Minimum two. I think two will be more than enough to create the XOR. I think two is enough.
Okay.
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 Now, this is a simple idea about this perceptron that if you want to create the classification for the nonlinear function, you need to have more than one layer. Okay. Uh, now, let's go a little bit further and let's say your perceptron has nonlinearity as well. That means you have some input and that input is passed through some sigma and then you are getting the output. So output is basically sigma of W transpose X. Oh, sorry. Okay. So basically, in this case, you wanted to create a non-linearity, and then you want to basically, since this is not linear, then we can call it non-linear, right? And if that sigma is passed through W transpose X and sigma is appropriate enough, in that case, this XOR can be predicted using one layer
Single
as well.
perceptrons.
Yes. And if it is something like a square, here you have 0, 0, and here you have 1, then basically you can map like you have 0 here, you have 0 here, you have 1 here. Instead of creating two lines, you can basically create a non-linear function. And you are saying that if you're trying to map this 0 onto this nonlinear function, this will go here. So 0 will come here, 0 will come here, and 1 will come here. And you will say, if I will create a single line, then I can basically uh, classify this nonlinear into a single layer or a single perceptron in this case, right? So from here, the idea of kernel comes into the picture, or increasing the dimensionality comes into the picture. So let's talk about the kernel or dimensionality. So let's take a very classical example. In this case, you have, this is one class, the second class is around this. And you are saying that if you will create a circle around it, it is just this is a 1D, and we are just doing it for the 2D. Okay.
Mhm.
So in this case, you have the x1, you have the x2, and you know that for the classification, you need a circle. So you are saying that if I had the relation something like x1 square plus x2 square, you would have said, you would be saying that if x1 square plus x2 square less than 0, or plus some k less than 0, then I would get this W1.
This class
Otherwise,
W1.
I will get the W2.
Yeah.
Right?
Yeah. W2.
So, yes. So basically, you can, basically in this case, you have a x1 and x2 as an input. So you will say that I will increase my dimension, increase the dimension such that my first dimension is x1, the second dimension is x2, and the third dimension is x1 square plus x2 square, such that I have a linear relation between all these three dimensions, and I can still get the network in a single layer. I can still able to classify this using a single layer, right?
Right.
So what is happening? This non-linear function is actually taking the input, squaring it, and adding it. Function is basically, if it is taking x1 plus x2, x1 and x2, it is doing this. And this is the nonlinear function, right?
Yeah.
So, and this is also called in some sense a kernel that can create a 3D, I mean, you can project it, the x1 and x2 onto this, and you can create a plane, and that plane will be function of x1 and x2, and that will able to, I mean, plane means a linear function, and that function will be of function of this kernel f, and that will be able to classify this nonlinear function, right?
Sorry, what
So
do you mean by
this
kernel here?
kernel is something that takes some input and it is mapped to the different dimension. Kernel is
How
like
how it is different
mapping
from
from
the
input,
how it is
mapping
different from
from,
percept from? Go ahead, please.
no, kernel comes a very fundamental concept in the machine learning when there was an, like, people don't want to use neural network because they have some idea that they can create a relation between input and output without creating a neural network. So they
Okay.
came with the idea of this kernel,
Okay.
then where they can map their inputs to another dimension, higher dimension function,
Mm.
such that
Got it.
that higher dimension is a function of itself, the input, and they are able to classify that. Okay. So this kernel is, this is basically they write K. So this is the kernel that takes the input x1 and x2 and create the mapping in the third dimension, that is called as x1 square and x2 square. Okay. Any confusion?
Clear, clear. Yes.
I mean, the people does not talk about the kernel these days because they are directly going into the deep learning without having some experience in the machine learning. There are a lot of problems that doesn't need the deep learning. Or even when the deep learning came into the picture, people before that were able to solve the nonlinear classification, right? And that was because of this kernel idea of kernel, mapping the inputs into a nonlinear function and calling it as a kernel. So basically, it is creating another dimension for the input. Okay.
Okay.
Yeah. So this was the overall idea. So I mean, it's 7:30. Let's say some question. So there next week I will talk more about the neural network. What is the width? Uh, what is the universal approximation theorem? And there are a lot of concepts. So for I think this is the overall I have overall for this week has been covered. I think you should not have any confusion, right? Okay.
That's great.
Yeah. So let's see some questions.
Question we can ask for the previous session as well, or this only?
You can ask like if I am answering, you can ask anything. I mean,
For
it's
example,
not that.
can you give example of regularization in the total loss function, which is
Yes. Okay.
okay.
So let's solve this question. I will come to that in the later, in the last.
Okay.
Okay.
Okay,
About
sure.
the regularization, right? Okay.
So this was taught in lecture 15, 14 and 15. Yeah.
Yeah, I will come to that later.
Okay.
So let's do it a little bit. So these are the questions that has been used as a assignment in the previous run of this same course. So I will just go through it and let's see how much you know. And
So
so
this is for
given
this year or previous
previous
session?
year,
Okay.
not like this is the question that has been like if you can say I'm not sure the year is not given. It was in the 2022. The same course was
Okay.
enrolled, and whatever the questions was there, I'm showing you. And
Okay.
in the similar fashion, you can basically solve the this year questions. So it's, it, I am just giving you the idea.
Okay.
So once you have the experience here, you can solve the similar questions that you have to submit till Wednesday. Okay.
Okay.
So a given cost function is a form of z theta where theta is square minus theta plus 2. What is the weight update rule for the gradient descent optimization at t plus 1? Consider alpha is equal to 0.01. Answer? Uh, anyone?
For A,
Yeah. Yes. So basically, you are taking the gradient with respect to theta, that is 2 theta minus 1. And this is the alpha, that is 0.01. So A is the correct answer, right? The second question is, okay,
What is the question? Can you identify
can
which
you
one of the
identify which
graphs
of the
gradient
following?
descent will not work correctly? I
Yes.
think so. C.
Why not option? Why not? I mean, why not B? You are talking about the options, or you are talking about the figures.
Figure.
So second doesn't have the optima as
Even
well, right?
second also having multiple
No, they have the
with
saddle point. So you cannot. This is called the saddle. If you know, the saddle is being
Mm.
used on the horses, right? And
Yeah,
that's
yeah.
from there the saddle point come. The name came.
first one is the
So you
convex.
Yeah, first one is the convex, and these are the saddle
And third
point.
one is also
Yes. So
convex, no?
basically, if you will try to create a point from here to here, you will cut the function into multiple, right? You create a line from here to here,
The
you will
second
create,
figure.
yes. So the option A is which of the following will not correctly. So second figure, first and second figure, and the option is in the fourth figure. So basically second figure, right? According to the options. Okay. This is another question. So from the following two figures, can you identify which one correspond to the batch gradient descent and which one to the stochastic gradient descent? So anyone
Second one
without,
is a batch. First is
yes,
the first is
Graph A is
the
the batch one.
graph.
Batch.
Graph A. No,
no,
graph B is a batch.
yes. So A is the batch basically, and second is the stochastic gradient descent, right? Or but let's talk in the sense, yeah. So there is a, if you are saying stochastic gradient descent, you are already assuming you are using some kind of batch, mini batch. When you are saying the batch gradient descent, you are using all the data. So graph A is a batch and graph B is a stochastic. Okay, under confusion?
Okay. Mini. Okay, I got confused with mini batch. Okay.
No. So batch is basically using all the data, and the stochastic already uses the mini batch. Okay.
Mini
So
batch.
option A is the batch gradient descent, B is the stochastic. So option A should be correct, right? Yes.
Yes.
The question is, suppose for the cost function j theta, the 0.25 theta square as shown in graph below, in which the point in which point do you feel the magnitude of weight update will be more? So A point 1, 2, 3. Anyone? The question is, on which point do you feel the magnitude of weight update will be more? Means there will be a larger gradient value.
Point
Anyone?
one.
Point
Yes,
one.
Gradient
one
will
is a
be
larger
point one
gradient,
will be
right?
maximum.
Point,
Point one.
Maximum.
Yes,
point
yes,
one.
yes, right. Thank you. So point one, that is a red point, and option A should be the correct, right?
Hmm.
Yeah. So which logic function can be performed using two-layer network, neural network?
XOR.
Right now,
XOR.
A-
XOR.
Actually, minimum or even and also we can do with two layer, right? But XOR is needs minimum two layers. Is that the question? Then XOR is the answer.
yes, yes. So that's how you have to play with the language. Otherwise, you will get confused.
Yeah.
I mean, you
Minimum
can
then
also have a two layer for and,
exactly.
but the value of
Exactly.
W will be 000, something like
Yeah,
that, right?
exactly.
So all of them are correct.
Yeah, you are see, that's what.
Yeah.
If they use minimum, then XOR is the correct answer.
Yes, yes. I think I've already alarmed everyone that always look into the language of your question. Otherwise, you will suffer.
You're right.
So let X and Y be the two features to discriminate two classes. The value and the class level of these features are given further. The minimum number of neurons layer required to design this neural network classifier.
1 second.
So we can see we have the two classes. We have 5 input
1, 2, 3.
pairs. So basically you can draw it on your notebook
Yeah, drawing
and
0
yeah,
to 1 second, please.
take a time and please give the answer.
Plus 1, W1, and 2, 2, And 1 3 is class 1 and 1 minus 3 is class 2. Okay. So I think so one neuron should be sufficient because
So are you
on the
able to
top
classify using a line only?
one line, yes.
Yes. So we need one neuron,
One
right?
neuron.
One neuron. So option A is correct. Yeah.
Yeah.
Everyone, please try. Okay.
Yeah.
The question
Can you
is,
please explain it? Answer.
It is linearly separable actually. So 3 points, say class W1 are coming on top of the XY curve, and one curve is on x is equal to 0 and one is below. So that's why they are linearly separable. Maybe if you draw.
like, try to draw on a XY graph,
Yeah.
and
Yeah.
for every point, write the class value, like 1 or 2,
Oh,
and
okay.
you should be able to create a line between those two classes. If you are
Linear
able to do that,
classifier.
then yeah.
Actually, minimum number of layers means how many number of linear classifier we are having. That many number of neuron layers.
Yes.
Yes, you're right.
The question is, which among the following options give the range of the logistic functions? So if you
Logistic
remember,
means log, right? Log, right?
no, logistic is basically a kind of soft max function. That is 1 by 1 plus a to the power minus x.
Okay, then it is like a 1 plus 1 by 1
1 by,
plus e power minus x, e power minus x.
yes, yes.
So -1 to +1 actually is a binary kind of function.
No, so,
0 1 0 1. C.
right, yeah, yeah,
C.
0, 0 and 1.
Yeah.
So option C.
C.
Yeah, so option here is the amount of weights to be learned by neural network having 3 inputs and 2 classes as output, and you have the 5 neurons in between. So how much total W are needed? That W includes the biases as well. So let's say if you have a 3 input and then you have a 1 bias, so basically you have a 4 input, and 4 input are given to 5 neurons. So basically you have a 5 times 4 20 weights, and then you are having
Number is,
5 in you have a 2 classes as output. So 5 times 2 is basically 10, and then you have a 1 bias, right?
one
Am I
second.
correct?
The number of no, unable to understand the question. Sorry, to be very honest. The number
Yeah.
of
So
weights, including
yeah.
bias.
So try to have a picture in which you have a 3 input,
Okay.
like 3 nodes at the input. I mean,
Mhm.
not node, 3 input, and then you have a in one layer you have parallelly 5 hidden layers, and then you have a 2 output.
Yeah. Could you please draw it? Is it possible for you to draw?
Yes. So let's go to another question. Then we will discuss about it
Okay.
later. Okay.
That's okay.
Yeah. This is the correct way to discuss the
Oh,
previous
okay.
question.
Okay.
So you have a here we have a 2 input, and if we have a 2 layer and the 1 output,
Mhm.
replace it with 3 input, 5 layer, and 2 output. Now give the answer.
For X NOR function, activation
No,
function is not the
no,
same.
like let's solve the question number 8. But take this picture as an example. So here we
Oh,
have the
okay.
2 input. So instead of having 2 input,
Instead of three,
assume
two. Mhm.
yeah, assume 3 input. Instead of two
Okay.
hidden layer, you have the 5 hidden layer, and you have
Okay.
a 1 output here. So now we have the 2 output. Now try to find it, the answer. I will do it. I want all of you to participate.
So which is the hidden layer here? Is it A1, A2?
This
Is the
A,
hidden layer?
yes,
A1,
yeah,
A2.
these are the hidden layers. So we have the 5 such hidden layers.
Okay. Could you scroll up, please? That question 8. Yeah, 3 inputs. But they're saying with 3 inputs, right? But you are saying 2 inputs, correct?
No, in that picture we have you have 2 input. Just
Okay.
I just gave you a picture for the understanding what you have to calculate. So okay, should I solve it or you are going to solve it? Because I gave you the picture what you have to do.
25.
So this, so you are getting 25.
Five. 3 into 5. 5 into 2. 10, if I'm not wrong, 10 should be the answer.
No, I think it is around 30, I guess.
3 into
no,
5.
30 not.
Sorry,
I mean
3 into
32.
5
It
into
is
2.
32.
3 into 5 into 2. 50, 30.
No,
Do we have answer 30?
No, the answer will be 32. Let's explain
Okay.
it. Let's learn.
Oh, there's
So
a
you have
bias
a 3
also, right?
input.
Bias
Yeah, we
also.
have to.
Bias.
Yes. So you add that. You have to add the 2 biases of the output
Two
as well.
biases, yeah. So 3 into 5 into 2 plus 2. Yeah. Like that. So 3 is the input layer. 5 are the hidden layers, right?
No,
So
not
3
like
into
that.
5.
Okay.
Oh, okay.
So you have a 3 input plus 1
Okay.
bias. So basically you have a 4 input overall, right?
Hmm.
And you have a 5 hidden layer. So overall you have a 24 cross 5 is basically the 20 weights.
Correct.
Because each one is giving 1 W, right?
Okay.
To 5, all the 5. So you have the 20 weights here, and then you have a 5 hidden layer and you have a 2 output. So basically for the 2 output, the each one is like each
Given to 2.
I mean uh, each output is taking 5 inputs from the 5 hidden layer and
Yes.
plus 1 biases. So basically total 6 input are taken by each output. So you have a 2 output. So basically 12 output. It is given to here this outputs. So basically 20 plus 12 is basically 32.
32. 32.
32 is the correct. Yeah, that is correct.
Yeah. So basically 20 plus 32. Understood?
Yeah, we got it.
Yes.
Yeah. Yeah. I just wanted you to think. Otherwise, I could have explained. Yes. Yeah. Here the question is
For the X node function as given by this, the activation of function of each node is given by X more than 0, more than 0, 0 and 2. So X node, right? For X or you have X node.
so external function given.
So it is 1001, correct? So X1, X2, 1, 0, 0, 1. So two lines will be required. So that means X1 plus X2.
Basically, you have to do the multiplication addition, right?
1.5. Okay. Okay.
Yeah,
Here.
like I'm not sure if you are able to see all the numbers. Are you able to see all the numbers here?
Yeah. 0.5 minus 1 minus 1 minus 1.5 1 1 1 1
And okay.
and
I
minus
think this is
0.5.
minus. Yeah. So whatever the output you are getting, that is the answer, right? Nothing complex, right? So I will just skip it.
One second.
Yeah,
0.5.
go on.
So for example, if we take from the top one, there is 0.1 weight, correct? 0.5 weight. So 1 into 0.5 plus hidden layer into 1. Like that only, right?
Yes, like
So
you have
0.5.
the x2 is 0, so ignore the x2 for right now. We're doing nothing here in this case.
Okay.
So basically you have 1 into 0.5. So
Into
0.5
1 minus 0.5.
into minus 1. So basically minus 0.5 is the output here.
But
Okay.
X1 is also nothing, right? X1 and X2 both are nothing, right?
No,
Because
x1 is 1 here.
Okay.
x1
okay.
is 1 here. 1 is multiplied with -1. And here 1 is multiplied with 0.5. So basically overall it becomes minus 0.5. Minus 0.5 is going as a input, as
Okay.
output here at the A1. And in this case, 1 from 1 minus, I mean 1 into
0.5.
minus 1.5 is minus 1.5. And plus 1 into 1 is basically minus 0.5. So minus 0.5 coming also here. So minus 0.5 into minus 0.5.
0.25.
I'm sorry. Minus 0.5 into 1 is
Minus
minus
0.5.
0.5. And this is basically getting added. So this is becoming.
1 second. The weight is 0.5, right? The first one between +1 and A1 is 0.5 or minus 0.5?
Oh, it is 0.5, I guess.
0.5. No, miss, I cannot read clearly. That's why I'm asking.
Let's see the answer.
0.5 into 1 plus minus
Okay.
minus 1.
Okay. One more thing. Like whatever the output A1 and A2 are creating,
A1.
we have to pass through this function f as well. Okay.
Okay.
Yeah, each node is given by this function. Okay. So we are not assuming this. So basically this was giving minus 0.5 and this was also giving minus 0.5. So this will become 0 according to this function, given this function is non-linear. And then this 0 is the input. So we will get minus 0.5 as the output. I'm not sure this is 0.5 or something. I'm not sure.
It is a bias, right? So minus 1.5.
I think this is minus 0.5.
Okay, I'm getting minus 1.5. Maybe I'm
Where? Here or here?
output x1, nor x nor x2.
No. So basically, read here that whatever the output you will get at A1, that will pass through this function f.
fx. Okay.
So you are getting the negative value. So the output will become 0.
You
are
become
getting the
0.
negative value.
Okay, got it.
And here you are also getting the negative value. So you will become 0.
0. Okay. So C. Got it. Okay.
Sir, can you please explain the previous problem, sir?
Yeah. So you are getting the
number 8.
output minus 0.5 here, minus 0.5 here, and that
Should be
minus
0.
0.5 is passing through this function f, and it is producing value 0. Right? Because the output is negative. So whatever the input is negative, so the output will become 0. Right? This is like a step function.
Only for positive it will carry forward. Only for positive it will carry forward. All negatives
No,
it will
only for
become
positive
0.
it will become 1. It will not carry forward.
Yes, sir.
One.
It will become 1.
Yes.
Or if
Sir, can you
given
please
already
explain
x1
the
equal to
previous
1 and
problem,
x2
sir?
equal to
Question 8.
so we can take that.
Yeah.
x1
One by
equal to
one.
1 and
Yes.
so we can put
Yeah.
that and we
x1
can
is equal
solve. We are getting 0.
Yes. So basically, when I'm keeping the value of x1 1 and x2 0, I am getting the output a1 and a2 as a minus 0.5 and minus 0.5. And that output is passed through this function f, and that is giving us 0. And that 0 is taken as the input. And when we are passing that, we are getting the value minus 0.5 here as well. And that minus 0.5 is passed through that function f. And it is producing the value 0. Here it is clearly written that each node has this
fx.
Okay. So this is the non-linear function after the network output. I think I have already discussed that, right? So if you have a perceptron and the output is passed through that non-linear function.
Sir, can you please explain the previous problem, sir? Question number 8.
So basically the input was 3, output is 2, and you have a 5 hidden layer. So in this case, in question 9, you have a 2 input. So replace it with 3. You have a 2 hidden layer, replace it with 5. And you have a 1 output, replace it with 2. And then you should be able to solve it, I guess. So basically, you have a 3 input and then 1 bias. So you have overall 4 input. and 4 input is passed to each hidden layer. So basically, you have a 5 hidden layer. I mean, in one hidden layer, you have a 5 node, in some sense. So you have each input is passed to one node. So overall, you have a 20 node. And each node has a 20 weight, and each weight has some value. Okay. Now you have got the 5 output. 5 output is passed to uh, overall output here, the final outputs, the two classes. So each classes is taking 5 output from the hidden layer and one biases. So each output class is taking 6 input. So you have a 2 output, so there will be 12 inputs. So 12 input means 12 W values and the 20 W values here. So overall you will have a 32 W values. I hope you have no confusion.
Okay, sir. Thank you, sir. Bye.
Yeah, try to draw it. And so once you will draw once or twice, it will be very clear. Yeah, this question is not so good. Yeah. Which activation function is more prone to vanishing gradient problem? Okay, I will come to this. Just see the option for right now: ReLU, TANH, sigmoid, and threshold. Okay, let me stop sharing and come to this. The question is, which one is prone to vanishing gradient? I mean, this question should come later, but okay. The first was, I guess, soft mix. Let me check.
ReLU, I think so. They have mentioned ReLU.
And it was ReLU. Then another was TANH, sigmoid, and the dy threshold. So this looks like something like this, whatever I was talking right now, we were discussing. So
Sigmoid
we'll have a
is
value
1 by 1 plus e power minus x, right? Sigmoid.
Yes,
That is
the logistic
this
function.
sigmoid.
Yeah, the logistic function.
Binary function.
Yeah. This is the sigmoid. Okay. And then this is the TANH. This is 0, this is 1. TANH, it is -1, 1. Okay. And this is the ReLU. Okay. Okay. So idea is, like, if you'll see the 10h looks something like this: e to the power x plus e to the power minus something. I'm not sure. Plus is, I think, here. Okay. This is the 10h. So this comes with the exponential. So when you will try to find the gradient, let's say the gradient of this will look something like this. Yeah, go on.
So the function whose derivative is the same function, I think so that has the minimum, right?
Yeah, I mean, let's say the derivative something look like this. Okay, I just do something.
The first one is constant, I think so. The first one will be constant.
Yes, I mean,
y is equal to mx plus c kind of thing, which
it
is
will look
constant
something like this.
Constant.
It will look something like this.
Yeah.
I'm just drawing the derivative and it will become 0. Okay. Right? So the yellow one is the derivative and the red one is the original value.
Original value.
Yeah. In this case, they are providing the answer 10h, but
I think so. Threshold should be the correct class.
I mean, this is, first of all, this activation function is discontinuous.
Okay.
This is
They are
discontinuous
providing,
as well.
they are providing
Yes.
answer is Relu. Relu, is it?
No, answer is they are showing 10H. So I will come to 10H. Let's talk
Okay.
continuous. Okay. So there are different way of taking the gradient for this uh, this ReLU and the threshold, because at one point when you have a discontinuous, like let's say this is your, so if you are going plus epsilon, your gradient is this. If you are going minus epsilon, the gradient is this. So basically you have a multiple gradient at a point.
Mhm.
I don't know, I should exclude this. Is it a part of a question, or I mean, this question itself is a vague, to be very honest. I would not answer this question if I were a student. Okay.
Okay.
Here the gradient is zero, here as well. However, I mean the gradient is, sorry, gradient has some value. Here it is zero and here is some value. And here is zero everywhere. So, and in the case of 10H, this gradient is much steeper than the sigmoid. Like if you are trying to calculate the gradient, it will look something like this.
Mm.
Okay.
Mm.
If we have no alpha here, assuming that, okay.
Mm.
And if we have a sigmoid saying that I have 1 plus e to the power minus x. Okay. In
Mm.
that case, tan h would be answer, because the gradient is becoming nearly zero for the input, which are even smaller compared to the sigmoid, which has a gradient. I mean, for this input, the gradient is higher in this case compared to the tan h. Okay, and I'm not sure all of you know about the vanishing gradient. So when we train the neural network, in the process of training, we calculate the gradient of dl by tw, right? W are whatever we are trying to train, because this is what we are changing, right? And while calculating this, we go through a lot of, let's call it like this. We have the intermediate values, and we go through this chain rule. Okay. And in the chain rule, if any one of these gradients becomes very low, the overall multiplication of the gradient will be very low, right?
Yes.
And in that case, you will not be able to update the value of W. And that is called the vanishing gradient. In this case, if you are multiplying these gradients and you are saying that the value of this is 0.0001 or 0.001, basically you are changing the W by this factor, right?
Mm.
Alpha into this.
Rate of change of loss function with respect to W is very low.
Yes.
Mm.
And in that case, whatever the iteration you are keep going, because this gradient itself is just very low, the W will not change even though you will go 10,000 iteration, 20,000 iteration, because every time you are getting this value very low. And that is called the vanishing gradient. Okay. And since we are using all these gradients, we are having this unknown activation function into this neural network that takes input, does all this addition, multiplication, pass through sigma, and gives the y. This sigma should not have a very steep gradient, or whatever this input the sigma is taking, it should not be very far. Otherwise, it will produce a very low value for the gradient. Okay. So I would not answer this question but the idea of vanishing gradient come into the picture. So you should just return with what this concept called. Okay.
Okay.
And now you are talking about the regularization. I will just so when you are calculating any loss function, you are calling this as a right.
Yes.
This is loss function, and you want that this theta should not be very large. Let's say this loss function has been trained. I mean, let's write something k. This loss function has been trained, and you are getting some theta, or you are saying that whatever the theta you are getting, it should have a minimum value. Like I was discussing in the last class, like uh, you are training a y equal to you are having a classification problem. You are having a classification problem. You want to get the value of this. Uh, you can say you want to get the value of this W.
Linear classification. Okay.
Let's take this value of like W1 and W2 or W or B. You want the value of W2, W and WB2 minimum such that this classification happens and you don't get this value of W and B if you are doing the same thing next time. So basically you are using a regularizer for W and B such that every time you reach the minimum of W and B such that if you are doing the same experiment, every time you will, I don't know why I'm repeating the same thing again and again, but every time you reach the minimum value such that when someone asks you to reproduce this value, you should get the same result. The science is all about the reproducibility, right? When you are doing some kind of optimization, you have given some result to someone and you are saying that I have got this value of W and V, and I should be able to classify uh, these two classes, but he told you to do the same in front of him and you got some value of another W and V, and he's asking like, okay, you earlier you said this answer and now you are giving me this another answer. How should I believe you? Once your problem is not the simple enough. If the problem is simple enough, you will say, see, I am satisfying this criteria. But you have a multiple class, your data is way too noisy. Okay. Okay. And there is another concept that I was talking earlier about the overfitting. This regularizer comes into that picture again. Like when you are solving any neural network, you have some data and you want the value to be such that this doesn't overfit for you. In that case, you will have to say that this should be minimum enough such that my loss stabilizes as well as I don't overfit. Okay, this is the overfitting. So in that case, you will use the regularizer for the W such that it does not exactly fit the. Otherwise, you don't know when to stop. Since you are seeing that you are training a neural network, or you are saying that you are seeing that your loss is going to 0. Okay, but when you predicted for some new value, you got some this value. However, you should get this value, so you are occurring an error. Uh, and earlier you assumed that since your neural network is giving the overall loss as a 0, you should get the correct value, but you are not getting a correct value. Your error is getting there, right? Sometimes your error will be very large. Let's say if you are trying to predict here, you will get way too far. Right? This is the error.
Okay.
So in that case, you will use the regularizer on the W such that you never overfit this. You never go beyond what you want. Okay. So
Yeah.
the regular these are the some everyone will tell you, but these are the someone you should understand fundamentally. Okay. Yeah, I think this is it.
Thank you. Yeah, thank you. I think so. Just I'll share my screen. The eighth question is something like this, correct? 3 layers, and it is, and for 5 hidden layers, correct? And two classes, isn't it? The eighth
Yes.
question. And
Yeah, but you
these
have
are
not created the biases correctly. You
no
should try to
bias.
create.
This is one bias.
No,
And
bias are
this is
given to the hidden layers, not the inputs.
okay.
You will,
It is here, is it? Okay.
yes, and every neuron will get out. Every like hidden layer
No.
node will get one bias,
One bias, okay.
and there two as well. Yeah, you already have two biases. Assuming
Yeah,
you
here.
have two output.
This is not there. This is not there.
No, this is not. Yes.
So how many weightages are there? Correct. So these 3 into 5 into 2, 30 plus 5, which is 35 plus 2, 37. Ideally, 37 should have been the answer, isn't it?
No. So you have a 3 input here.
Yeah,
and
3.
you have a 5 output. I mean,
Correct.
let's call this as output.
3
So
into
this
5.
you will have a
3 into
15.
5. 3 into 5,
15 plus
15.
5 is 20.
20. Okay.
Plus 10
20
plus
into,
2.
20 into, okay, got it. Got it. 3 into 5, 15 plus 5, 20. 20 into 2, correct?
20
40.
plus not 2. Why you are multiplying it? You have to say
This
5
is 2
into
plus
2. So 5 into 2, that is 10, plus 2, that is 12, and plus earlier you have 20. So basically overall 32.
32. Okay. Got it.
Maybe I will explain in the next class using
Yeah,
some
yes.
matrix.
Okay. Sure. Okay.
So yeah.
Plus 10 plus 2, I think so. Yeah. 15, 20, 32. Yeah, that is correct. 32.
Yes.
This is the correct
So
answer.
I
Okay,
will
sure.
stop the recording
Okay.
and everything will be within the recording. You can.
Thanks a lot.
What is happening? Just give me a minute.
Thanks a lot for your session.
Okay. I will just cancel this. Sure, what
Thank
is
you.
happening? Okay, you can leave it.